Now, we've been saying all along that entropy is about measuring disorder in a system. So we need to start to think about numbers now. Okay, it's a quantitative analysis of the order or disorder. So there must be some kind of figures involved. Okay, typically with enthalpy changes, we're talking about a difference in enthalpy between the reactants and the products. But with entropy, we have something called standard molar entropy, and that is a measure of the disorder of a substance. So there are absolute numbers. Obviously, there are standards, but the numbers exist. Okay. Up to now, we've discussed really the change in entropy of the system, which is about if disorder is increasing or decreasing, if there are more arrangements of the particles present or more arrangements of the energy quanta, then the entropy of the system, delta S system, will increase. But to determine whether a process is spontaneous, we need to consider the delta S tot, the total entropy change for that process. And to do that, we have to bring in the idea of the change in entropy of the surroundings. Okay? So when a system is reacting, then it's either using up energy from the surroundings or it's giving out energy quanta to the surroundings, and that's changing the entropy of the surroundings. You can imagine if you're giving energy to the surroundings, you're increasing the number of arrangements of energy quanta, so you are increasing the entropy. So we must bring this term in. Now this also explains why endothermic reactions, some of them can be spontaneous, and exothermic reactions don't have to be spontaneous, because the total entropy is dependent on these two terms. And we'll see that. We'll see how that works relatively soon. The system entropy we can calculate using an equation a little bit like the enthalpy change for a reaction when you have the standard enthalpy of formation of the products and the reactants. So in this case, to work out the change in entropy of the system, the delta S system, we do the calculation, the sum of all the entropies of the products multiplied by their stoichiometric coefficient, so the number that's in front of them in the chemical equation. So the sum of all of the entropies of the products minus the sum of the entropy of the reactants. That's fairly straightforward. Where do we get these entropies from? These standard molar entropies, we get them from tables, from data tables. Delta S of surroundings, so the change in entropy of the surroundings, is calculated by that expression. Very simple expression. Where delta H, obviously, is the enthalpy change for the reaction. Interestingly, it's in joules per mole, because we're going to be working with joules in these equations. So joules per mole. And temperature has to be in Kelvin. It's the absolute temperature. It's a lovely, simple, elegant expression. Okay, now, what does this say? Well, for an exothermic process, if delta H is negative, then delta S for the surroundings is going to be a negative times a negative, positive. Okay, so for an exothermic process, the entropy of the surroundings increases. For an endothermic process, as this is positive, then this becomes negative, the entropy of the surroundings decreases. Energy is absorbed from the surroundings, there are less or fewer energy quanta, and so the entropy of the surroundings decreases, which is important. So like we say, the total entropy of a change is going to be a playoff between these two terms. Have a look at the worked examples on page 65 of the textbook to give you a bit more background to this. Now, this is quite an interesting table, and the equation obviously that we're working with at the moment is that equation. So essentially, if you look at these terms mathematically, then if the entropy of the system, the change in entropy of the system is positive, okay, and the process is exothermic, which makes this term positive. So if this is positive and this is positive, then the reaction, the change will be spontaneous under all conditions. Now they call delta S tot delta S universal, but that doesn't matter. So if the enthalpy change for the reaction is exothermic, it's negative, and the system is positive, then it will always be positive. Okay. Let's jump down to number 4, which says if the enthalpy change for the reaction is positive, that makes this term negative, and the entropy of the system is negative, then delta S total will always be negative. So the reaction will be, well, it won't be spontaneous under any conditions. Okay, because delta S total is negative. Remember, for a reaction to be spontaneous, delta S total must be positive. And then for exothermic processes, this term will be positive. It will depend on how big the entropy change of the system is and what sign it is. Okay, so if you've got a negative delta S system and you've got a positive delta S surroundings, then it's a playoff between these two things. Okay, to make this term more positive, we could use a lower temperature, because mathematically, if the temperature number is smaller, this term gets bigger. So you often find that for exothermic processes, where delta S total is negative, then the process tends to be spontaneous at lower temperatures, because mathematically this term becomes more important, more significant. For endothermic processes, where this term is going to be now negative, the change in entropy of the system is positive, then we want this term, because this term is negative, we want this term to be less significant, so we want T to be very big, so that this becomes less significant, so delta S of the system dominates. So in this case, with an endothermic process and an increase in disorder, so an increase in delta S of the system, the change will be spontaneous at higher temperatures. And that's a lot to take in. They're the 4 possibilities, but have a think about that. It's something that will take time to sink in. Let's look at some specific examples. Okay, so there we've got our 2 equations here, which we're going to use in all of these examples. So, dissolving ammonium nitrate in water. Okay, it's fairly simple. So you've got a solid ionic lattice, and it breaks down to give aqueous ions. Delta H is positive. Now this is spontaneous at 298K, so now we have to try and explain why it is spontaneous at 298K. We know that, it's a given. In the crystal lattice solid ammonium chloride, there's lots of order. Okay, so this is low entropy. The ions are in fixed position, so the entropy is low. When the ions go into solution, the entropy of the system increases because there are many more possible arrangements of the particles. Okay, so the entropy of the system increases significantly. So delta S system here is positive. Right. Delta S system is positive, and delta H is positive because we said it's endothermic, then it's going to depend on how big each of these two terms are. Now in this case, because this process is spontaneous, obviously this term is outweighing this term. In this case, what would we want the temperature to be? To make this term less significant, we want the temperature to be higher, wouldn't we? So that this number becomes less significant. Okay? Let's have a look at this equation. Now let's look at the state symbols, which is always going to be important when we're talking about the entropy change for the system. So we've got aqueous, solid, more aqueous, liquid, and a gas. So if we look at that system, it's clear that there is an increase in entropy of the system because we've got much more disorder on this side. This is an endothermic change, but it is spontaneous at room temperature. Okay, and for that to be true, obviously we have to have an increase in the total entropy. So there's a large increase in the entropy of the system, and that's because of the gaseous carbon dioxide forming, and that outweighs the fall in entropy of the surroundings. So let's have a look at this. Delta S tot is, we know it's positive here at 298K obviously. Delta S system is very positive. Delta H is positive too, but that makes this term negative. So overall, which wins? The delta S system wins here, and this reaction is spontaneous. Here's one of the old favorites from key stages 3 and 4, burning magnesium, very bright light. You light it in a Bunsen burner, don't you? And it burns intensely and exothermically to give magnesium powder, solid magnesium oxide. So we've got a solid and a gas producing a solid. Let's have a look. Let's do some calculations here. The enthalpy change for this reaction is highly exothermic. Be careful here, this is in kilojoules. And the entropy change of the system is negative. Why? Well, if we've got a solid and a gas producing a solid, we're actually increasing the order of the system. If the order is increasing, then the entropy is decreasing. So magnesium oxide, a solid, has a lower entropy than the reactants here. So we know delta S of system is negative, but we know this reaction is spontaneous. So delta S total must be positive. And for that to be the case, well, we've got an exothermic process, haven't we? So this becomes positive. And at temperatures that are quite low, because we want this term to dominate, then this reaction will be spontaneous. Okay, now we can do the calculations, put the numbers in. Delta S of surroundings is minus delta H over T. Remember, this has got to be in joules. Delta S total in that case is the delta S of the system. There it is there. I'm sorry, there it is. I know they've done this the other way around. Sorry. Delta S of system is there, plus the delta S of the surroundings, which is minus delta H over T, which is there, and that gives us a plus 3890 joules per Kelvin per mole, joules per mole per Kelvin. So it's positive. So delta S total is positive, therefore this system is spontaneous. Okay, there's a very large increase in entropy. Thing is, it's not visibly spontaneous at room temperature. What do we need to do? We need to give it a kickstart, don't we? And that's where the Bunsen came in. The reaction is feasible, it's spontaneous, but you need to supply a lot of activation energy to get the reaction to start and the magnesium to burn. But remember, the definition of spontaneous was the process will continue, once started, will continue without any further external influence. Okay. Now we can't assume that a feasible reaction with a positive delta H tot will happen at a particular temperature. There are other factors involved. Okay. In this case, we talked about the activation energy to get the reaction to start. Right, have a look at those pages, read them carefully, and do all of the questions.